The clip today is about using motion graphs to get information. So we will look at distance, displacement, speed, velocity, and acceleration from either looking at the position versus time graph, velocity versus time graph, or an acceleration versus time graph. Also, I want you to be able to use the graphs qualitatively to identify change in direction, changes in speed, and finally, I want you to be able to sketch the motion graph if you have some description. So let's get started. Let's start with an easy question. What's the velocity at t is equal to 3 seconds? Okay, take 1 second to think about it. First thing to do, look at the axes. X on the vertical axis, t on the horizontal axis. So if we want the velocity, classic way to think about it is that velocity is position over time. So then at 3 seconds, if we look at it, we have a position of 0 meters. So this would mean 0 meters divided by 3 seconds. And that would give us a velocity of 0 meters per second. Don't fall into that trap, okay? This is clearly wrong. And the reason it's wrong is because when we want to use velocity, the definition is the change in position over the change in time. So really it's not x that goes there, it's delta x. So now if we look at it more carefully, we can take 2 points. So let's say the point at 3 seconds and a second point that will be the point, let's say, at 0 seconds. So these are our 2 reference points, and then we have 0 meters at 3 seconds, 60 meters at 0 seconds. We subtract one from another, and then you see that we get minus 60 over 3, so we get minus 20 meters per second. So that value corresponds to the slope of that line. So when we're dealing with the x versus t graph, we can look for the slope to obtain the velocity. What if I have the same graph, and I'm asking you again what's the velocity at t is equal to 3 seconds, but this time we are looking at the velocity versus time graph. Then it's actually much easier because really it's just reading the graph. So we look at 3 seconds and we can see that the value that we have there is simply that the velocity at t is equal to 3 seconds is equal to 0 meters per second. What if I ask you what's the acceleration at t is equal to 3 seconds? Well, finding the acceleration on the velocity versus time graph, well, again, we know that the acceleration is the change in velocity over time. So this is once again just the slope. So we can take our change in velocity and the change in time, and we get, not surprisingly, the same number as before, but this time it's an acceleration instead of being a velocity. So we can conclude that on a velocity versus time graph, the slope will give you the acceleration of the object. But how do we deal with this if we have a line that is not straight, but it is curving? How could we find the velocity at point P now? That's not as obvious. So I want to use a small GeoGebra simulation to explore this with you. The idea is not complicated. All right, if we want to have the velocity at point P, what we can do is to take 2 times that are close to the time where we want to look at the velocity or find the velocity. And then what we can do is to narrow this interval. So we can take these points and bring them closer and closer together so that it will be a better and better approximation of what is the velocity at point P. Eventually what will happen is that we will get the velocity at point P or at time t. And this is the green line here. All right. So you see that this green line is on something called a tangent line. Tangent line, again, is a line that is matching the curve at the given point so that it's barely touching it without crossing it on that region. Okay, so it's the same as what we would get for the average if we get our points closer and closer together. So as the blue point gets together, you see that they will match eventually the instantaneous velocity. So in situations like this, whenever you want to find the average of a quantity, you want to look for the slope of a line segment over a time interval. While when you want to have the instantaneous value, you will look again for the slope, but it will be the slope of the tangent line at one moment in time. So at one point, for instance, point P. Now I want to discuss the different shapes of graphs that we will see. Because it quickly gets complicated and to avoid using calculus all the time, we'll restrict the motions we study to those involving constant acceleration. This will simplify the equations and the graphs and will allow us to discuss things more conceptually. It might seem like a terrible assumption, but actually there are many motions that can be approximated with a constant acceleration. And I want to use a GeoGebra app, a simulation once again, to show you what type of graphs that you should be expecting. So in this small app, we can see a position versus time graph, a velocity versus time graph, and an acceleration versus time graph side by side. I want to start with 0 acceleration. That's the simplest case. And if also the velocity is 0, then it's the trivial graph that it's just that the position stays constant. Position could be positive, could be 0, could be negative. It all depends on what's the initial position of the object. Then slightly more interesting, if your velocity is positive, then what we see is that on the position graph, we now have positive and constant slope because the velocity is constant. Once again, the initial position is something that is arbitrary, that we can choose to be whatever we want. Finally, with still a constant 0 acceleration, we can also have a negative value for the velocity, which means that now the position versus time graph will have a constant but negative slope. Then we could have cases where the acceleration is constant and positive. Now you can see that it's the velocity that will have a constant slope. And the position versus time graph will now be a curve. And that curve is a parabola. So the parabola, its shape or its opening will be defined by the acceleration. However, what portion of the parabola we see and what it looks like will depend on what we choose for the initial velocity. And if we have an acceleration that is negative, it will be the same kind of features that we will see, but this time the parabola will be opening downward. Let's summarize all of that. So for the acceleration graph that are at the top row in here, we know that we'll always have a flat line, an horizontal line. Either it will be at 0, positive, or negative. For the velocity versus time graph, what we will get will always be straight line, but this time there can be an inclination. So either the velocity will be constant, or the velocity could be increasing, positive slope because acceleration is positive, or the velocity could become more negative, negative slope because the acceleration is negative. Finally, for the position graph, there is essentially 3 big categories. If your acceleration is 0, the position graph will just be a straight line, either with a positive slope or a negative slope, depending on the velocity. If the acceleration is positive, then we will have a part of the parabola. The exact shape or portion of the parabola we will get will depend on what's going on with the initial velocity. That will define whether it's going down at first or going straight up. And what I want you to remember is that if the acceleration is positive, then this means that the parabola will be curving upward. Parabola is happy. Afterwards, we have an acceleration that is negative, and this time we will get a velocity that has a negative slope. And the parabola we will get for the position will once again be defined by the acceleration and the initial velocity. But this time, because the acceleration is negative, it will actually frown. Okay, so in the case of a negative acceleration, we have an unhappy parabola. So opening up or opening down, depending on the sign of the acceleration. I want to wrap up this clip with one last method that we can use to extract information from a motion graph. So I want you to imagine the following. A car moves at 20 meters per second and passes in front of the origin at t equals to 0 seconds. What will be its position at 10, 20, and 30 seconds? Well, it's not super difficult. We know that the car moves at 20 meters per second, so this means that in 10 seconds it will cover 200 meters. And since it starts at 0 meter, we know that after 10 seconds it will be at 200 meters, after 20 seconds it will be at 400 meters, and so on. So we increase by 200 meters for every 10 seconds. We could have a more general formula that would just state that the position, in this case, would be equal to the velocity versus time. Be careful, this is a simplified formula that only works for this particular case. But what I want you to think about is how could we see that information graphically? So here's a simulation by Tom Walsh on GeoGebra that let us explore this a little bit better. So what I want to do in here is reproduce the problem that we're looking at. So I have the car moving at 20 meters per second for 40 seconds. And what you can see is that the 800 meter corresponds also to the area under that curve. So if I take my 20 meters per second times the 40 seconds, that's essentially the area of this rectangle. So when we want to look for displacement on a velocity versus time graph, what we can do is to look for the area under the curve. However, this is a fairly simplified version. So what if we have a curve that is a little bit more complex, something like this one in red? So which area under the curve would you pick? Would you pick the one that is shown in A, in B, and C, or none of these? Okay, so pause, take a few seconds to think about it, and then come back and we'll discuss it. So I hope you have your answer. If you answered D, you are correct. So if you answered D, you are correct. So let's see why this is the right answer. It's something that is a bit confusing sometimes. The problem is that area under the curve is actually a misnomer. It should really be called the area between the curve and the zero axis. So what we want to do is we want to always use these three ways to delimit the area that we want to take. The first condition is that the area must always touch the v equals to 0 axis. So this means that you always want to have one line that is on top of the v is equal to 0. Then the area must always touch the curve, so that's the line in red in here. And finally, if you need to, in order to close the area, you can always have vertical lines. So in here I should have one vertical line that is going in here and a second vertical line in here. And these are the limits of my areas. So afterwards you can just shade in the area that you care about and it should look something like this. Just a couple of notes to add on that. So first note, the area and negative velocity count as negative if you try to calculate the displacement. So for instance in here, the first area here is for negative v. So when you want to calculate the displacement, you would have to subtract this area, all right, because it's going backward. And the other note is that this trick is also applicable to to get the change in velocity from an acceleration versus time graph. So if you had acceleration versus time, the area under the curve would then give you the change in velocity. So I hope this clip helped you to understand how to extract quantitative information from velocity versus time graph, position versus time graph, and acceleration versus time graph. We will look a little bit more of that in the next clip. Just a few notes to add to that. First, when the area is in the negative velocity side, you have to count it as negative if you try to calculate the displacement. So for instance, in here, this area in here would count as being negative for calculation of displacement, because essentially for that portion, the object was going backward. Also, the method that we just described with the area under the curve is also applicable if you want to get the change in velocity from an acceleration versus time graph. So if you have A versus t graph, then the area under the curve is just the change in velocity. If you need more practice, I suggest that you go to the GeoGebra simulation that I used in the previous slide. With this clip, I hope that you're able to do quantitative analysis of graphs. In the next one, we'll look at how to sketch graph and also how to do a little bit more qualitative description of what's going on with these motion graphs. Thanks.